Good day everyone, my name is William Pittman and I am the General Manager of AMC in Toronto and a Principal Geotechnical Engineer. Today's webinar looks at geotechnical risk associated with narrow vein mining operations. We will be going through a series of slides which highlight some of the factors that need to be considered with narrow vein mining and which have a bearing on risk. To start, let's look at some of the areas where geotechnical risk occurs. I've provided some examples of key areas of risk. This list is not exhaustive, and we shall be visiting other areas of risk during this webinar. I have split the application of risk into two categories, operational and long-term, which includes closure. Operational risk involves such things as dilution, equipment selection, ore recovery, and productivity, including costs. Long-term risk involves such things as mine development lifespan, crown pillar stability, and possible loss of the mine reserve in such things as pillars. The photograph on this slide shows the Hollinger Golf Course in Timmins, Ontario, which is in Canada. This area was impacted by the collapse of crown pillars left above narrow vein gold mining. So where is geotechnical input required? The answer is essentially throughout the life cycle of the mine. As with any project, laying the foundations for good input is essential, and we will be covering this aspect in more detail. Good geotechnical input is needed when the project is at all stages of study, from the preliminary economic assessment right through to the feasibility and detailed design stages of the study. Good geotechnical input is also needed at all stages of mine planning, from the life of mine plan right through to the short-term planning aspects. Good geotechnical input is also needed during operations, when looking at ground control designs, providing management with effective ground control management plans, and in detail when operational advice is required. I like to emphasize that at the end of the day, geotechnical engineers are, to the best of their ability, providing safe solutions to, more often than not, very complex situations. It's all about risk and safety. An all too frequent dilemma, however, is from the question, do we really need to heed geotechnical advice, especially if it compromises our production or reserve? In my opinion, the answer is yes. We do need to heed this advice, and if we don't, then the consequences can be extremely adverse. However, I do agree that geotechnical risks and consequences should be assessed and prioritized so that informed decisions can be made. So, what can go wrong? The following photograph was obtained from the internet and is indicative of the sort of risks that can occur. Of course, this is a buried scoop in a stope. Okay, so rock can be difficult to engineer. Why? The answer is that rock is impacted by mining in a number of ways. Firstly, rock is a highly variable material in the first place in terms of strength and because of inherent discontinuities such as geological structure. In addition, mining is dynamic. In fact, it's a very dynamic process. We are constantly changing conditions, for example, by blasting. We create damage zones around excavations from blast fracturing. From stresses, we change the stress regime within a rock mass when we excavate material. The air itself can be a changing factor. Air from ventilation can degrade rock strength through the process of slaking. And of course, water. Water from drilling, as well as groundwater, can impact rock strength and can also lubricate geological structure, for example, which can lead to failure. It is important to understand that even if we understand typical conditions, unusual situations still occur in mining. For example, where we intersect major faults or where the alteration zones may impact the characteristics and behavior of certain areas of a rock mass. Also, the geometry of an excavation is often dictated by geology and the requirements of economic extraction. This aspect will be covered when we look at rock stresses. Okay, so what do we need to provide good geotechnical input to narrow vein mining projects? The answer here is that good geotechnical information, and I stress good information, is needed throughout the life of the project. The process should begin with good early data collection, and this should include geological, geotechnical, and hydrogeological information. This data should be collected well, organized well, and presented well, and should have been validated through a defined and auditable process. This data is then used for subsequent analysis and often is used to provide input to rock mass classification and numerical modeling. I've also mentioned good observation. This aspect is often overlooked in the often schedule-driven data collection phase. By good observation, I mean using all available information from such things as rock outcrops, existing excavation, road cuts, and the like. All of this will then lead to good safe designs, which will include factors of safety and risk. These factors need to be justified and defendable. Okay, so we have collected some really good data, we have assembled the data, and we have prepared a geotechnical model and some good defendable inputs to geotechnical tools that can assist us with the mine design. Now we have to ask ourselves, what elements of the mine design should we be focusing on? Where is the risk? I think we should have a good understanding of any potential surface underground interactions, such as between an open pit and underground operation. We should try to gather information about rock stresses, as often this information is difficult to obtain with any certainty until underground operations are well advanced. For example, have there been borehole breakouts or core disking observed during exploration drilling? These can be identified by using tools such as televiewers or by good inspection of the core. This information is then used for mine planning, which will need justification of such things as interlevel distances, standoff distances, extraction sequencing, pillar sizing, dilution, and backfill design. When looking at underground surface interaction, I've put in this example, which is from the Rutan mine in Manitoba. In this instance, the crown pillar was removed prior to completion of underground mining, and this is shown in the photograph here. The region experienced an exceptional storm event which led to the inundation of stopes with water. This led to liquefaction of the hydraulic backfill in the stopes and subsequent barricade failure. This in turn led to inundation of some of the underground workings with backfill. The lesson here is the timing of crown pillar removal and possible risks associated with this. This slide shows the transition of a mine from open pit to underground. In this instance, the open pit was in saprolite and underground mining of stopes had commenced. A key question would be, what thickness of crown pillar do we leave and what influence will mining have on this? The geotechnical data is telling us that the rock quality in the crown pillar area is not that good. The risks here are that we leave an inadequate thickness of crown pillar. This ultimately will impact both the underground stability, but also possible impacts on the stability of the open pit slopes as well. As I've mentioned previously, another factor to take into account are rock stresses. These are difficult to determine before you get underground, where you're able to take measurements from the underground excavation. But the key point here is that we do need to understand rock stresses and the impact that they may have on mining. This is particularly true the deeper mining gets. The slide here just demonstrates that a stress regime is altered when excavation takes place, and different areas of the rock mass will either be in compression or tension, and those may change as mining progresses. And that is shown in this slide here. Essentially, you have some development and a stoping area. You can see on the left-hand side the stresses going through the rock mass. Once we mine a new stope, then stress conditions can change, and in this instance, in the footwall development, we've gone from a compressive regime into a tensile regime. And this can change depending on the sequencing of your stoping, for example. So stress is really a key factor when looking at narrow vein mining. The next few slides show how stress influences underground excavations. This is important as this impact will impact costs and schedules. The slide here shows a breakout from a raise bore due to high stresses. You can see here what's termed dog-earing in the excavation. You're going from essentially a circular profile to one which is more oval. And this is a result of the high stress regime that is impacting this excavation. I think what this slide also shows is when you have these conditions, the amount of rock support that you then have to put in to make this safe for access can be quite a daunting thing. This example just shows stress-induced fracturing or spalling. This has impacts again because you then have to support this, and yet again this will have impact on both costs and schedule. This is an example of wall buckling. The stresses and the geometry of the excavations, as well as the geological characteristics of the ground that you're in, has led to buckling of the rock itself. This has huge impact on development, rehabilitation of those excavations. It also has a great impact on things like dilution, where significant buckling and rock mass failure can lead to excessive amounts of dilution and serious mining problems. Stresses also impact pillars. In this example, we're seeing what's known as hourglassing of pillars. Essentially, that pillar is beginning to fail. You get loss of dimension to that pillar. The stresses then get shared onto abutments or adjoining pillars, and those in turn, if they're overstressed, can lead to further failure. And you can in fact get a domino effect of failure across quite large areas of ground. Of course, that then subsequently leads to serious mining problems. So what do we need to consider from a design perspective? Key aspects where the design needs to be justified include things like interlevel distances. This is a key parameter that drives stope stability, which is difficult to change once it has been set. Standoff distances, which is the distance from stoping to the major infrastructure, such as ramps. If we get that wrong and you get excessive impacts on that development from the mining, that can lead to expensive rehabilitation. Extraction sequencing. This is essentially the scheduling of stopes. This needs to be done with the effects of stress taken into account, normally using numerical modeling. So it needs to be an iterative method where designs are made. You have a look at the impacts on different stoping sequencing and see what impact that has on the stresses and how things like the footwall development is impacted. We need to look at pillar designs for the crown, sill or rib pillars, for example. And again, these need to be based on defendable geotechnical inputs. And as I've mentioned previously, dilution certainly needs to be considered. Dilution can be complex. There are various things that need to be taken into account, not only geotechnical but also mining. For example, blasting, how efficient and effective your blasting is will certainly impact your dilution. So all of these factors need to be taken into account when looking at mining of narrow vein ore bodies. That's the end of this very brief webinar. I hope I have provided some basic information and some items for thought when it comes to thinking about geotechnical risk for narrow vein deposits. Thank you for listening, and please feel free to contact me with any questions. Thank you very much.